Hi, good morning. This is Trina here to discuss about the first law of thermodynamics. So this is the second lecture of the thermodynamics chapter, and today I will tell about the first law of thermodynamics and the special forms of the first law and the relationship with the enthalpy. And also you will learn to solve the problem of thermodynamics. That is very important. And if regarding the lecture, if you have any doubt, you can communicate with me through my email ID or my mobile number. So these things are given in my personal information. So the most important part, that is the course page. Here I have uploaded entire study materials, the probable questions, semester questions, and the solved problem. So I hope that already you have joined with the given code DMBC, and when you join with this code, then you can access entire study material. So the course chemistry, the subject code is CH101 for odd semester, CH201 for even semester. And this subject is for undergraduate BTech students, and the streams are CSE, IT, Civil, Mechanical for even semester, Electrical, EC, BME for odd semester. Credits are 3, contact hours 35, and the weekly I will take 3 lectures. Here the prerequisite knowledge required, that is the 12 standard. And about the course objective, you will learn the several concepts of chemistry. And in the course outcome, the students will apply the fundamental concept of thermodynamics in different engineering application. So here the entire lecture plan is given so that you can understand that which topics will be covered in which day, and so that you can take the prior preparation with the course material already uploaded. And in the class, during the class, you can do the interactive session. So today I will cover the module 2, the use of free energy in chemical equilibrium. It is the use of free energy in chemical equilibrium. So already you have learned in the first lecture the basic concept of thermodynamics. Okay, in my first lecture you have learned the basic concept of thermodynamics, system, process, properties. So what you have learned? You have learned that what is the thermodynamics, what are the application of thermodynamics, and different systems like the open system, closed system, and isolated system. Also, you have learned the macroscopic properties, the intensive property and the extensive property. And in the process, you have learned different process like the reversible process, adiabatic process, isothermal process, isobaric process, isochoric process. So all these things already you have learned in the first lecture. Why I am telling this? Because all this knowledge is required to understand the next lectures. Okay, so today I will cover the first law of thermodynamics. It is already highlighted, and enthalpy. So now I will tell about first law of thermodynamics and enthalpy. So you know that if any work is done or any heat energy is transferred. So in our universe, from the law of conservation, no heat energy or no work can be destroyed or cannot be created. Okay, so from this concept, this is the first law of thermodynamics. This is the concept of first law of thermodynamics. So what is the first law? It states that energy can be converted from one to the another with the interaction of heat, work and internal energy. But it cannot be destroyed or created. Okay. So from any energy, like say mechanical energy, you can convert into heat energy. You have learned these things. Or like any work can be converted in form of the heat energy. But no energy can be created or destroyed. So from the mathematical expression, how we can derive? So we can say that W proportional to Q. So what is W? It is the work performed. W is work performed. And Q, what is the Q? Q is quantity of heat produced due to this work. So this is proportional. So W or Q can be interchanged, but nothing can be created or destroyed. So now W proportional to Q. If we like to equate that W is equal to, then we have to bring a constant, that is Z. Okay, Z is constant here, and Z is the constant of proportionality known as Joule's mechanical equivalent of heat. J is the conversion factor for mechanical energy into heat energy and vice versa. And if say W in the Joule, W the unit of work done is in Joule, and the heat energy in calorie, then J will be equal to Joule per calorie, that 4.2 Joule per calorie. So now, what is the internal energy? In thermodynamics, the internal energy or intrinsic energy of a system is the energy content within the system. Okay, within the system, there is the energy content that is called internal energy or intrinsic energy. Example like liquid freezes into solid yielding heat energy. The above example shows us the existence of internal energy. Now, internal energy of a system may be defined as sum of all possible type of energies, like say kinetic energy. Kinetic energy are different types like translational, rotational, vibrational, the kinetic energy, and the potential energy. So due to the interaction with neighboring constituents, nuclear energy, chemical energy. So all these are the stored energy. They are called the potential energy, and the moving energy, that is called the kinetic energy. So the sum of this kinetic energy and potential energy is called as the internal energy. Now, it is denoted by either U or E, capital U or capital E. So, you will see in different books, it is writing in different way, either E or U. So, both are correct. Both are the representation of the internal energy. So, unit of internal energy, that is the SI unit, internal energy, Joule. Now, if for a system When a system changes for thermodynamic state A to thermodynamic state B, its internal energy will also change. Okay, so we are taking the thermodynamic state A to state B. So their internal energy will be changed. So we take that UA that represents the internal energy of state A, and UB of state B, that is the internal energy of state B. Now, the internal energy change will be calculated as UB minus UA. So that can be written as del U. That is the change of internal energy from the state A to state B. Now what will be then, how we will write the first law of thermodynamics? So here we will write that Q is equal to E, that means del E or UB minus UA plus W. Okay, that is the form of first law. And the internal energy has different characteristics like number one, internal energy depends on the current state of system but does not depend upon the path used to arrive the state. Okay, internal energy, that is why it is not the path function, it is the state function. Number two, the internal energy of a system is an extensive property. Okay, so you have learned what is the intensive property, what is the extensive property. So extensive property, that means which depend on the mass. So it is the extensive property. Number three, what is it? So number one you got, 2, 3. There is no change in internal energy in a cyclic process. That is the cyclic du is equal to 0. That means if it is a cyclic process, that means it comes at the initial state, then there is no change of the internal energy. Number 4, internal energy of a system depends upon temperature, pressure, chemical composition, volume, quantity of substance. Next, the internal energy of an ideal gas is a function of temperature only. Now, the next one is, during any transformation, the total energy of the universe remain constant. So I told that internal energy, that cannot be created or cannot be destroyed, it remains constant, only it can be converted in the another form. So now what I was telling, that the first law of thermodynamics, if we write in the form of internal energy, that will be Q is equal to UB minus UA plus W. Or you can write it is in the form of del U, or you can write del E. Both can be the representation of internal energy, either U or E. They are the representation of internal energy. Okay, so you got the first law of thermodynamics. So here we can write Q is equal to del U plus W. So Q is the heat energy, W is the work done, and del U is the change of internal energy. Or we can write Q is equal to del U plus PdV. PdV, it is for the mechanical work. W will be equal to PdV. Now, this first law of thermodynamics have different forms for different condition. So I am giving few examples for different process it will have the special forms. Like say for adiabatic process, what is it? You have learned, that means you can understand that it is required to for the first law of thermodynamics. You have learned in the first lecture that adiabatic process means there is no heat transfer. So change of heat energy will remain same. That means dq will remain same. That means q is the 0. So if q is the 0, we can write u is equal to minus pdv. Next, take the isothermal process. So isothermal process, that means there is no change in the temperature. So delta T is equal to 0. Okay, del T is equal to 0. So del U will be equal to 0. And if del U is equal to 0, so we get Q is equal to PdV. Next, take the adiabatic process. So adiabatic process, it is the Q is equal to 0. So you got that U is equal to minus PdV. Okay, so same way you can do for differently. You will try it in your home for the isochoric process, for isobaric process. What I have told in the last week, the different process. So you derive the form of the first law for all this process. Okay, so it is your home task. So now, what is the heat capacity? So the amount of heat required to raise the temperature of 1 gram by 1 gram of a substance by 1 degree Kelvin is called its specific heat. The heat input required to raise the temperature of 1 mole of substance by 1 degree K is called molar heat capacity or simply heat capacity, and it is denoted by C. C is equal to dq by dt. C is equal to dq by dt. Okay, so you have understood that what is the heat capacity, the amount of heat required to raise the temperature of 1 gram of substance. So if we take the unit amount of substance and we increase the temperature 1 degree Kelvin, then the amount of heat required is called the heat capacity. Okay, so if we do at constant volume, so we write it as CV, and if we do at constant pressure, we write as CP. Okay, so here you can see, but dq is a path function, and so it depends on the path and its value depends on actual process followed. So at constant pressure and constant volume, so you can see here that CV is equal to dqv dt. So it is the constant volume, and Cp is equal to dqp dt. It is the constant pressure. Okay, but du is equal to dqv, you know that, and dh is equal to dqp. So the constant volume, at the constant volume, we can write that del u is equal to Cv into del T, and del H I will tell later that it is the change of enthalpy is equal to, we can write Cp delta T. Now, which one is greater, Cp and Cv? So, Cp minus Cv, if we write the expression, we can derive that is equal to R. So we can say that R is the, you know, that universal constant, it is greater than 1. So we can write the, sorry, it is greater than 0, and we can write Cp is greater than Cv. So Cp is higher than Cv as R is the positive value. Now the enthalpy. What is the enthalpy? Enthalpy is a thermodynamic quantity equivalent to the total heat content of a system. Okay, so it will tell the total heat content of a system. It is equal to the internal energy of a system plus the product of pressure and volume. So by definition, we get that enthalpy is equal to internal energy plus the product of pressure and volume. So that is very important. So it tells about the total heat content of a system. Okay, now the characteristics of enthalpy, that is the enthalpy is a state function. It is an extensive property of the system. So it is not the path function, it is the state function. It does not depend on the path. And it is the extensive property, so it does not depend on the amount of matter. Now the mathematical expression for the change of enthalpy. So you have written here that H is equal to U plus PV by definition. So H is equal to U plus PV, or we can write dH is equal to du and dPV. So dPV we can write, if we write the d, that is the d, then PV, okay, PV, then you will get PdV plus VdP. Okay, so constant pressure, if the pressure is constant, that means if the pressure is constant, so dP will be equal to 0. So we get dH is equal to CV dt plus PdV. How we are getting CV dt? Because we know that du is equal to CV dt. We have got it earlier. So the mathematical expression for change in enthalpy for ideal gas, that is dH is equal to du plus PdV. Okay, so you have learned the definition of enthalpy and the expression of enthalpy. And the unit of enthalpy, that is the SI unit, Joule, for the SI system. Now, very important part, that if you want to calculate the enthalpy of a reaction, del H. So what will be the enthalpy of a reaction? So the difference between the sum of the enthalpies of the product and the sum of enthalpies of reactant, that is called the enthalpy of a reaction. Okay, so how you will calculate? The enthalpy will be equal to, enthalpy of a reaction will be equal to the sum of enthalpy of the product minus the sum of enthalpy of the reactant. That is the enthalpy of the reaction, the total enthalpy of the reaction. I told that enthalpy means the total heat amount of the system. So here you can see in the above reaction, N and M are the coefficients of the products and reactants in the balanced equation. Now, from the figure you can see that if the exothermic reaction, in which a system releases heat energy to the surroundings, then del H will be negative. Del H will be negative. Okay, so here you can see the energy level. It is the reaction coordinate. First you are drawing the reaction coordinate. Okay, that is the reaction coordinate, and here it is the energy level. It is the energy level. Now the product, the energy of that means enthalpy of the product minus enthalpy of the reactant. So you can see the energy level of the product is higher than the energy level of the reactant. Okay, so if you subtract here, you will get the del H. Okay, so if del H is negative, if del H is positive, that is the endothermic reaction. It will absorb the heat energy. If del H is negative, then it is the exothermic reaction. That means it will release energy. So now, what is the endothermic reaction? For the endothermic reaction, in which a system absorbs heat from the surroundings, so del H is positive. Okay, if del is positive means the product energy level is higher than the reactant energy level. That in this case, the del H will be positive, and that is the endothermic reaction. That means it will absorb the heat energy. And when the energy level of the product will be less than the energy level of the reactant, then the del H will be negative. And this case you got this is the exothermic reaction. Okay, so both the case the figure is showing the here the same. Okay, so you get this equation. Okay, so for the exothermic reaction, basically the product energy level should be lower. Okay, now you solve a problem, then you will be more clear how to get the energy level of a reaction. So here a reaction is given, that is, using standard thermodynamic values, calculate the enthalpy of the reaction of the combustion of methane gas with oxygen gas to form carbon dioxide and liquid water. Okay, so the reaction is given. We can write the reaction here. So here we can write the reaction, that is the methane plus oxygen. We know that CO2 and H2O will be produced. So here the enthalpy for each reactant and each product are given. Okay, so enthalpy for H2O, it is given minus 285.83. Okay, you have to multiply by 2 as it is 2H2O. Next is for the product CO2, the enthalpy value is given, that is minus 393.551 kilojoule per mole. So it is for CO2. So now for the reactant it is a CH4 and O2 is given. So for CH4, that is minus 74.87 kilojoule per mole. And for O2, that is 0 kilojoule per mole, and into you have to multiply by 2 as here it is 2. Okay, so you have seen it was given by M and N. So now you got the enthalpy of the products and enthalpy of the reactants. So now you subtract the total enthalpy of the products minus the total enthalpy of the reactants. So here you can see that we have it is the subtracted. First it is written the total enthalpy of the product, that is for CO2 and for the H2O. Next, subtract from the product enthalpy you subtract the enthalpy of the reactant. This is the CH4 and O2. So ultimately, you will get the enthalpy of the reaction. So you can see here that enthalpy of the reaction, you got the negative. So can you tell that it is exothermic or endothermic? Can anyone tell that it is exothermic or endothermic? Don't worry. Okay, it is given if del H less than 0, that is the exothermic reaction. Okay, clear? So it will be the exothermic reaction as the product energy level is less than the energy level of the reactant. So it will release the heat energy. It will liberate the heat energy. Okay, so if I summarize the today's lecture, what you have learned lots of things, like you have learned the first law of thermodynamics, how it is derived. That means any energy cannot be created or it cannot be destroyed. So from that you have derived the first law of thermodynamics, and you have learned different forms of the first law in different conditions, like isobaric condition, isothermal condition. Also you have got the homework, like you have to do for the isochoric and isobaric process. I have shown you for the isothermal and adiabatic process. And then you have learned the heat capacity, and for the constant volume, that is CV, and for the constant pressure, that is CP. And CP is greater than CV because CP minus CV is equal to R, which have the positive value. And also you have learned the enthalpy and the relationship with the enthalpy with internal energy. And also you have learned to calculate the heat energy, that means for enthalpy for a reaction. And you can determine the enthalpy of a reaction, and you also can tell that this reaction is exothermic or endothermic. Okay, so I hope that you have learned lots of things and you have enjoyed the class. So you go through the study materials, and if you have any doubt, you communicate with me. Okay, so thank you, and I am ending the today's session.